Hi, welcome to P6.1, Patterns and Relations. P6.1 is all about patterns and tables. So you can represent, you can correct them, you can find what's missing, you can look for patterns going up and down in a column. My pen isn't working. Or in a string of numbers going left to right. You can look at patterns in two columns. And you can create your own table of values for an equation that you're given. You can solve problems with them. You can graph them on one of those coordinate planes with an x and y axis and solve problems. I think we talked about that one already. Okay, on to this next slide. Remember back in about grade maybe 2 or 3, you talked about the input-output machine. And so the input-output machine is the same thing as this column over here, the input-output columns. If you took this 12 and you put it in this side of the machine would do some magical thing and turn your 12 into a 3. So what do you think the machine did? So you can maybe take some guesses. Well, maybe they divided by 4 because that would give you 3. Maybe that was the special thing that the machine did, divide by 4. So then you try that out on the next step in your table. Let's look at the 11. Can you divide 11 by 4? Nope. No, you cannot. So that's not the rule. Divide by 4 is not what the machine was doing. So let's look at some other things that they might have done to turn the 12 into a 3 and to turn the 11 into a 2. Maybe they subtracted. Subtracting 9 would give you 3. So maybe subtract 9 is what the input-output machine did. So you look at it with your 11, subtract 9, and yes, it is 2, so that is what our magical machine is up to. So we fill in the columns here. We're going to subtract 9 on all these other ones, and you can kind of see a pattern here going up and down as well. 12, 11, 10, 9, you know the next one's going to be 8, 3, 2, 1, 0, and you can even go into the negatives. Okay, let's look at our next input-output machine here. What do you think they did to the 3 to turn it into a 9? Well, maybe times 3, but that's not what they did here. That doesn't work. 11 times 3 is not 17. So maybe it's adding. Maybe they added 6. Use a different color here. Maybe they added 6. That works. And adding 6 works there too, so we just keep on going and we're adding 6 every time. 1 plus 6 is 7. Sometimes, like in this example here, these numbers aren't really in order. It goes from 3 to 11 to 2 to 1. They sort of jump around. So there is no real pattern going up and down. So you wouldn't be able to find a pattern going up and down on that side either. Let's look over here at this big yellow box. Sometimes in an input-output machine, or nice straight line. Oh yeah, I'm such an artist. You guys are so lucky. All right, sometimes they don't call them input and output. Sometimes they call it X and Y. So this is the X column and this is the Y column. Okay, so they just took variables. That's what X and Y are doing here. They're just letters that we use in the place of a number that we might not know. So what do you think they did to this X value to turn it into this Y value? What do you think the big machine in the middle did? Do you think they added 6? Okay, because that would give you 7. But 2 plus 6 doesn't give you 11. So adding 6 is not the magic rule. Let's look at a different one. Maybe they multiplied by something. Maybe times 2. And then 1 times 2 would be 2. And then they added 5, and that would give you 7. So sometimes input-output machines, these guys here, sometimes they can do 2 steps. So in this case, in this yellow box, let's try this on the next step. Times 2, which is 4, and add 5. No, that's 11, and that would make 9. Okay, let's try a different one. Maybe they multiplied by 3. Times 3 would be 3, plus 4 would be 7. So times 3, 2 times 3 is 6, add 4 is 10. Nope. Okay, let's try again. Maybe they times by 4. 1 times 4 is 4, plus 3 is 7. Let's try that here. 2 times 4 is 8, plus 3 is 11. Okay, I think we're on to something. Let's try it with the next one just to make sure. 3 times 4 is 12, and add 3 is 15. So the magic rule for this yellow box is multiply by 4 and add 3. That's what the input-output machine did there. So sometimes your patterns can have 2 different rules going on at the same time. P6.1, these are the vocabulary words that you need to know. So table of values, which is this guy here, and it can also be written up and down. And remember I said instead of calling them input-output, we're going to call them X and Y. That's usually what you'll see from about grade 6 on. So get used to the X and the Y. And you can tell here that it says Y equals 8 minus X. So this equals 8 take away X. Right? So just a different way of writing it. We could have also said up here, I'm not sure what the pattern is, I never figured out that one. If you get time, you might want to figure it out on your own. Anyways, these are both called table of values. So it's like an XY chart. Linear relation, I have a slide coming up on that, so we'll maybe leave that for now. But basically all of these things are related. You can take these XY points and you can plot them on one of these here Cartesian planes, and the y-axis is the one that goes straight up and down. The x-axis is the one that goes left to right, like the horizon, horizontal. In a line graph, that's what we've got down here. Linear relations are really anything that can be represented with a line. So this chart is showing us the cost of a cab ride, and he obviously starts at $4. He didn't start down here at 0. He started at $4. So as soon as you get in the cab, it's going to cost you $4. And if you go 1 kilometer, now we're up to $6. If you go 2 kilometers, looks like $8. So it looks like it's adding $2 every time you go up. For 3, now we're at 10. For 4, oh, might be a little bit more than $2, maybe $2.25. It's not exactly $12, is it? Okay, but anyways, the cost of a cab ride can be shown with a line, and so you can see the word line right there in the word linear. It just means that it's some sort of equation that can be shown with a straight line on a Cartesian plane, on a graph. A bar graph is what this colored guy is over here in the corner. And I think we'll go with a different color. There we go. A bar graph isn't quite the same. It can't be shown with a straight line because all of a sudden we have different values happening. So the y-axis is this one that's going up and down. It's labeled with numbers, but the x-axis is labeled with different kinds of pets. And so a bar graph doesn't even need to show numerical things, doesn't need to show numbers. Sometimes it can show amounts of hamsters or people who like yellow or whatever. So we've talked about the bar graph. X-axis, horizontal. Y-axis is vertical, up and down. The word scale. So let's look at this set of numbers down here on the bottom. They are going up. I just drew all over them because, you know, I'm such a good artist, like I just said. They're going up by 2. So the scale here is by 2, right? The scale on the bottom is 1 kilometer. So it's $2 on the side and 1 kilometer on the bottom. So the y-axis is showing money and the x-axis is showing distance, and that is the scale for that particular graph. But they're not always like that. Let's look back at our graph of pets up at the top. The y-axis is going from 1 to 10, and the x-axis is showing rabbits, dogs, cats, goldfish, and hamster. And so there is a scale on the y-axis, but there isn't really a scale on the x-axis up there. It's not numbers, so it can't really be called a scale. It would be called a label. The scale down here is just going every 1, right? And we're always starting at 0.00 in the middle. All right, next slide. We talked about patterns that have 2 rules. Now this isn't an XY chart like we had the input-output machine doing, right, like that. But there is something that's happening between the 3 and the 5. And because we've already told you there's 2 things happening, it's not just a simple matter of adding 2. Okay? Because the next time, well, they're adding 4. And the next time, well, they're adding 6. So you can see it's kind of an increasing pattern. I bet you if we added 8, we would get the right answer here, 17 plus 8. Right? Or you could say 3 times 2 is 6, take away 1 is 5. 5 times 2 is 10, take away 1 is 9. So times 2 minus 1 also works for this pattern. So there's 2 different ways to describe how to solve it. In the next example, it's alternating. So they're going to do something to the 1 to turn it into a 2, and then they're going to do something completely different to the 2 to turn it into an 8. And then they're going to go back to that the green rule, and then up to the top. So let's see if we can figure this out. To get from the 1 to the 2, well, maybe they added 1. Seems simple enough. What did they do to the 2 to turn it into an 8? Well, maybe they added 6. Okay, let's test those out and see if that works for the next step. Did they add 1 here? Yes, they sure did. And did they add 6 to get to the 15? Yes, they sure did. So sometimes patterns alternate. Add 1, add 6, add 1, add 6. All right, let's have a look down here at the bottom part. Plotting y equals x plus 2. So this is an example of an equation, y equals x plus 2. And all that means is they took the y value, whatever was here, and they said it's equal to this value plus 2. That's all that this is saying. So all the y values are equal to the x value and add 2 more. Okay, so let's have a look at their numbers and see how they did. Let's start with 0. If you're going to take the 0 value, that's your x, so it goes here, and now we're going to add 2 to it. And what is 0 plus 2? It's 2. Okay, so they showed the equation right there, and there's your answer. Now in the green section, they've said these can be described right here, this bracket, x, comma, y. Those are called ordered pairs. Ordered pairs. Okay, and those are what we plot on that coordinate plane on the XY chart. So once you get your x value, which we have right here, that was the 0 that we started with, and the y value, that was the 2 that we figured out. Then you can put them down just like this, bracket, x value, comma, y value, bracket. So those are your two ordered pairs, and when you go to plot those on a coordinate plane, the point 0, 2 would be right about, let's see, 1, 2, right about there, right on the line. Okay, let's do the next one. Let's do 1. It says that we're supposed to add 2. That's what the equation up here says. I'm going to add 2. So 1 plus 2 is 3, and these are our ordered pairs. We put them in brackets with the comma in between, 1, 3. So if we're going to plot 1, 3 over here on my handy dandy chart, we're jumping over 1 in the house 1 and up 3. Now this isn't super accurate because I'm just guessing where those numbers are, but hopefully you get the idea. So linear relations, think about relatives, they're related, right? Do you not love that sloth picture? It's an awesome family picture. So what this means is these 4 things are all related in a weird cousin-y kind of way. A table of values, that XY chart, right, where you've got numbers down the side, is, once you get those numbers filled in, you can turn those into plotted points, those ordered pairs, so that the 2 and the 5, we could say, well, that's 0.2, 5, and that can be shown on a graph. 1, 2, 1, 2, 3, 4, 5, right? That point right there. And if you did another one, let's do 1 and 4, 1 and 4 right there, maybe, I don't know, or there. That can be shown with a line. And the equation that goes with it looks like x plus 3. Yeah. So x plus 3 equals y. So I just made a quick little example, but all these things are related. Linear relations means a table of values, the XY chart, that can be plotted into ordered pairs, that can be drawn out on a graph and made into a straight line. That's why it says linear, has to make a straight line. And you can also show that what the input-output machine did is called the equation. So they're all just a lovely, happy, slothy family with really bad hair.